I'm Dale from Google, and I'm joined by Scott, also from Google, and Chris from NASA's JPL. Hey, guys.
Hey, good morning.
Morning. So let's see, last week I think I asked you what you were most excited about in natural language processing, and you gave me some awesome responses that gave me a lot to think about. And one of the things that I thought was very interesting was something that you said, Scott, which is what's fascinating to you is algorithms that scale with compute, because the idea is if you just add a lot more data, a lot more computational power, if it scales, then your model gets a lot more sophisticated. I think we saw a really good example of this in June when OpenAI released GPT-3. It was sort of all over the news then. It was this model that could do things, I think, blew a lot of our minds. This huge text model could write poetry, it could write code, it could do translation, all these things that it wasn't even designed to do, it was just really good at. And I think that's really made people's mind explode with all of the possibilities. I mean, Chris, you listed a bunch of different problems, extraction, search, all these different things that maybe a model like this could really help with. So I wanted to start this talk by jumping into the technology behind these models. How do they actually work?
Oh, wow. So we have a couple hours to go through this, right, Dale? So so you got your whiteboard, Chris. We'll kind of go through. Yeah, exactly. She's like, no, we'll turn you off. You know, the whole thing is, how do you represent words and language, inside a computer? And so we all grew up and we all learned parse trees. And I think, Chris was smiling in his preamble. There's the noun, there's the verb, and you create these trees. But there's a shift around 2015 where they said, can we have a more concise, denser representation? Because you can take all the knowledge of what a word means and embed it in a vector, right? So how do you take the knowledge of what a word means, like the word bank? You can bank your car around the edge. When you drive fast, there's a river bank, there's a little bank you go to draw out money. Same 4 letters, bank, but it has different meanings. So how do you encode all that and embed it in a vector? And there was a neat exercise called Word to Vec around 2015. And that was pretty neat. So what they did is they took it's called a one-hot encoding. So you have a vocabulary of 30,000 words. And you line up a 1 for that one word. And so you have a vector of a lot of zeros and a 1. And you squeeze it through a narrow neural network. And you try to guess the next word coming out. And so you get these networks that sort of shaped like an hourglass, right? And you take 30,000, you squeeze it through 100, and then you guess the next word. If you do this enough, that actually works. And so what's cool is you take the 30,000 and you embed the word, what that word means, into 100. That's kind of how it started.
So it sounds like what you're describing is one of the major changes in the way that we build these types of models is that we have better ways of representing words. Words as vectors, where vectors are points in space. Exactly.
And then so what was really curious about that in 2015 is that if you were to take that vector, the 100-dimensional vector, and even project it onto 2D, right, through, do a projection at 2D so you could plot these, or 3D, they started to have Euclidean properties, which was sort of freaky, right? So you had, you had queen and mother and female all and you can actually do a transformation and have that say male, king, and father. And they're like, that was kind of cool. Right. And so you started to see these relationships where they had Euclidean properties, and you could now manipulate words like vectors. And I think then, I think Chris and I started to talk around me, Chris, and then you got interested in this as well, right?
Yeah. The trick for me, is how different the process for doing this is today than, it sort of used to be. We spent so much time basically doing, like Scott was talking about, statistical models. That's kind of where I came up before I learned this, these dark arts and Horcruxes and all the stuff that we're talking about here and deep learning, and basically it's language modeling. And we did so much effort to basically take corpora and then pull in whether it's a noun or a verb, or the relationships between language, whether it's a noun or a verb. And we did all this labeling. And basically the difference now is that you don't need to do that today. You infer the relationship, basically you learn the features, and that's the benefit of these sort of black boxes, these neural networks, is that the feature engineering is all sort of automatic as opposed to sort of statistically generated before. And Scott and I tell you this too, Dale, is I'm just sitting here, it's like, oh, we're supposed to be the leaders in some of these, domains, and I'm just sitting here in awe, poor little boy here coming from a trailer, wow, I learned statistics and thought I was smart, and then now it's all doing it by itself. So
Well, then I guess if you're somebody watching, then you're in a good spot because you're on the cutting edge of NASA and JPL. So that's kind of cool.
Yeah, there you go.
So what I'm hearing from you, Chris, is that what's something that's different about these models today than the statistical models that you're used to building. I'm kind of hearing two things. So it sounds like the first thing is that, and I know this is true across a lot of types of modeling problems, is that it used to be that human beings had to do a lot more work to sort of set up these problems. They had to label nouns and words, and they had to do a lot of work beforehand before building a model. So does that part sound right to you?
Yeah, and most of that work was driven by sort of domain specificity and a high cost per label. You know, one of the big things in machine learning nowadays, one of kind of like the future, things that people are working on is learning with less labels. Like how can we reduce the cost? How can we make everything like labeling a cat video? And it's the same for text. It's like, how do we not have to have this big domain specific where you need a PhD in that domain, manual laborious effort to collect, curate the labels for structure? And how do we just, Scott's favorite thing, how do we represent like the brain or the eardrum or, our, basically visual cortex, cornea and things like that? How does biology inspire us to do it? And so it's a different way of model building. And it's actually at a much less cost on the labeling and the feature engineering part. Mm-hmm. And so that's really important for me. The more that we make basically machine learning require less labels without trading accuracy and all that, and it applies to text too, that's super powerful. Those are game-changing techniques.
This is a really relevant comment you're making, because somebody here in the chat says, well, in specific domains, trust me that you still need to label for syntax and semantics. So this problem of, oh, well, you can build something that understands general words, but how do you also do the same technique for a domain-specific thing? I think still a hard problem.
Yeah, I think, well, it's a very hot topic. I think, there's from 23 years ago, there was a neural network technique called an LSTM that was created, right? And way ahead of their time. And they had the way to sort of understand, how words change based on how they're used. Like we talked about bank before. If you look at how I use it in the sentence, the meaning shifts. And they built a neural network, basically a component that allows you to do that. But the problem with LSTMs is they're hard to do transfer learning. In other words, once you train it on one set of languages, it didn't transfer very well. And there was this breakthrough in 2017, which was sort of an evolution of word to vec, and people started to add this notion of attention, paying attention around you, and they generalized it. And what's interesting about that is they generalized it and they mapped the math to take advantage of GPUs in parallel processing. So if you were to do this by hand, you'd be like, my God, it's a lot of calculations, right? The LSTM is so much more elegant. If you look at actually the transformer, this model basically used high dimensional, basically parallel processing and really fascinating models to look around the context. And this now, you can actually do transfer learning on. And so what that means is you can actually have a model that's generic on train, like a GPT-3 or a BERT. And what you see in the chat, you can now take that, and we're seeing it, and learn domain specific ones. So in the industry, you'll see this is like AutoML is the current name for this, right? And the idea is you can take a generic model and then train it on a language for your domain, and you can own that piece. And that is really starting to capture the imagination of a lot of people. Because back to what you said, Chris, is that labeling everything else, if you have a model that can transfer learn on a smaller domain in just a few examples, that's astounding, right? And I think that's really sort of catched imagination. And now it's sort of a running up the bat in terms of who can do it fastest, right?
So you mentioned a couple of things here. So first of all, this idea of the transformer, so versus the LSTM. So the transformer is, like you said, it's this new type of architecture for neural network. It's the architecture behind GPT-3. And one of the things that you pointed out that's so unique about it is that it's easier to train computationally and do transfer learning on. Is that right?
Yep. I think it's really designed really well, such that the computations you do in a transformer map extraordinarily well to a GPU, right? And so these new devices. And so if you take an LSTM, it's elegant mathematics, and people tried to beat it for years, but it's so elegant, but it doesn't really work well on a GPU, because you're going between main memory and GPU, and you're shuttling back and forth. And they said, can we optimize this somehow? And so now you've got this mathematics. It's all about attention. There's a great paper called "Attention is All You Need," and it's a little provocative. But the idea is that you pay attention to the context in which your language is being used, and then you look at what you're trying to generate, and you can play off those two contexts to figure out the next thing to generate. And that is
I want to go into that, because this is a very interesting topic. What is so interesting about these new models is that they learn a ton. Most of what they learn comes from unlabeled data. That's a huge deal, because we have way more unlabeled text. All of the internet, all of Wikipedia is unlabeled text than we have labeled text. So can you talk a bit about how models learn from unlabeled text data, like for example, the corpus of all Wikipedia articles?
You know, I shouldn't be the guy answering this question. I'm supposed to be the space cadet, but I mean, I'll kind of tee Scott up, here or whatever. So, I shouldn't be talking about this next thing I'm going to talk about.
You are the author of the new upcoming TensorFlow 2 book, so I think that your expertise goes beyond just space.
Hey, let me figure out which way to point. All right, thank you, Dale. I appreciate that, and thanks for throwing the book out there. But yeah, so I got really into Spanish to English due to some work I was doing with the Defense Department and doing translation, for that. The amount of work that we had to do. I mean, I used to carry around, Philippe Cohn's yellow book, the big StatMT book, forever. It was the Bible. And you read the different steps in that book to basically train up a statistical machine learning model. You got to know all about the language rules, the grammar. You got to basically do parallel alignment of corpora, all of these steps, And so basically today, what happens? You need really parallel corpora, parallel sentences and things, but you don't need to know the grammar, the language, and the whatever, because really the design of these network architectures are basically set up to learn those things. And I'm gonna grab this baseball up here and throw it down, to Scott. But that's the basis for what he's about to explain.
So what you're describing is a pretty common trend in deep learning with really big data. It's actually kind of what we just talked about. How you don't need to specify as much information up front. How does the language work? What are the nouns? What are the relationships? Because the models can actually learn those things themselves.
100%. Right. Yeah, we call it Mad Libs. Go on, Mad Libs, Scott.
Mad Libs, that's Bert, right? Yeah, I think what's an observation is that our face, human language, regardless, and how humans communicate, they form a probability distribution. The eyes tend to be right next to each other, and there's a mouth, then there's a nose, and there's a mouth typically, and they have different sort of shapes. There's a distribution of faces. That's a probability distribution. Right. Same thing for human language, and how verbs and nouns and whatnot, that forms a distribution for a particular language. And now you're creating these networks that can learn that distribution, and not only learn it, if you give it a sample, it can generate stuff from the distribution. Right.
So take me from the face example to the text example. I need the bridge there.
Okay. All right. So think of, in English, the way we express ourselves and the way this language form is a statistical probability distribution. Right. In other words, if you say a verb, most likely you're going to say, an object of the verb next. Right. Or if you have, and so the idea is that instead of having to frame this, there's a pattern to how these sentences form. And there's lots of different patterns. And so when you have sufficient examples, you can start to detect these patterns statistically. And what's interesting about the transformer model is it sort of generalized a technique that's been going on for a few years, where it started with word to vec. That the idea is take a word, squeeze it through a network, and get a vector for it. And they said, well, you need to know more context, and they started to look at what's the words around it, right? So that the next thing word to vec is don't just do the next word, do the word before and after. That's trigram. And then Bert came along and said, no, that's what Chris said. Let's play Mad Libs. So Mad Libs was, let's sort of we'd use this model, and what we're gonna do is we're gonna take a paragraph, and I'm gonna knock out 5 words. You guess them, right? And if you look at enough paragraphs in Wikipedia, turns out the network starts to learn what the meaning of these words are, the context around it. And that was about 100 million parameters using this new architecture called a transformer. And what the transformer did is allows you to pay attention to the words before and after the words you're trying to understand, or the sentences before and after, right? So someone took Bert and said, wait a second, instead of words, how about whole sentences? So Pegasus was like, let me guess the topical sentence from a paragraph. And now now you have the ability to summarize a paragraph by guessing the missing sentence.
So what Scott's talking about here, by the way, is GPT-3 is the new hotness, but it really started with BERT, which was 2015, I think, right?
Yeah,
and then there are all these models.
2015. Yeah, and the transformer came, and then it did BERT, bidirectional
encoding. We're making all of these improvements. Yeah, and exactly. It seems like the improvements, in addition to the architecture, a lot of it's coming from the training task. How are we taking the data, and what are we asking the model to learn to do?
Yeah, that proves it's not just smoke and mirrors too. By the way, every one of us has our aha moment, and we cling to that moment like nothing else. So it's like, like I was telling you, Dale, when we were talking before, it's like for me, 2014, what I was doing, these DARPA MEMX things, nothing will ever change. Everything will be relatable back to that. So for Scott, it's going to be all relatable to Bert, and it makes sense because it is, and it's true because we said it on this Twitch stream. But that's everything. It has, we have our aha relatable moment. And so it all goes back to 2015 on this. So
yeah,
I actually had my own BERT, sorry, I didn't mean to pay you off, but I had my own BERT moment as well, because I started in Google research the year that BERT was released. And I just remember it being so interesting. I was building an LSTM, which you talked about, which is the
there you go. Yeah,
things,
they're
right?
awesome.
And
they
then,
still are.
and then the BERT paper came out, and everybody in my research was like, well, can we try this on BERT? And then everybody else and everywhere else in Google research was like, oh, can we do this on BERT? And then Google search was like, can we do this on BERT? So it really kind of spread like wildfire, at least throughout Google.
Yeah, and I think if you look at the transformers design, the mathematics to work in parallel processing, because you could parallelize and look at a lot of the words in parallel and try to figure out the weights of how much do you pay attention for each different layer of the network to the previous word, and you could build all kinds of attentional models inside the network in parallel. So that was super cool. But then, Rich Sutton, we talked about before, had this idea or claim that, maybe it's an observation really, is that the models that seem to be working best are those that are really taking advantage of compute. And so why not do something extraordinarily large? So to go from 100 million to 100 billion parameters, 175 billion, and on the path to 175 billion, it's very data hungry, but now you can look at different patterns in like an entire Wikipedia. And now we're finding those very, very large models are doing extraordinary things, right? Because these models, I guess transformers are the first thing that could actually scale to that scale. Right, you don't get vanishing gradients, exploding gradients, because now you've got these rich attention networks. You can look at broad corpus. So instead of looking at, the baby was like, look, word defect, the next word. Now you're looking at entire, hundreds of words or maybe an entire document and getting the context from that. And that is just so powerful. And I think we're just beginning to, this is just the third version. And now, right, I think we came out with a reformer. Oh, look, we can do it faster. Yeah, so I think the industry is now latching on and saying, how far can we take this, right? What else can we use in this model where by leveraging compute, what happens when you have an extremely large model?
My neural network is telling me that all of these components that we're building must be named ER at the end. It told me to pay attention to that.
ER at the end?
Yep.
I think your training sample's too small.
Yeah, exactly.
So I have a great question from the chat here about these types of models. But first, I just want to quickly summarize. So if we had to say like two bullet points that people take to understand, well, what is this new type of model that's been changing NLP? I'm going to say, based on what you guys said, it's this way of using unlabeled data for training, and this architecture that happens to scale really well with compute, happens to be really efficient. And these two things combined lead to these models that are much larger than anything that we had to contend with before. Would you guys agree with that?
That's what you do so well, Dale. I love it. And I think you nailed it, right?
I'm like an encoder, right? Like
well, it's GPT-4, Dale Markowitz.